All right, you're good to go.
All right. Hello, everyone. Welcome to another week of the Catalyst Breaking into the Tech Industry interview session. Today we'll be covering backtracking. I think generally, like if you ask anyone what their worst interview topic is, a lot of people I think will say backtracking. And so I guess today we're just kind of trying to dispel a lot of that lack of foundation, and hopefully you can feel pretty ready to face just a very general scope of backtracking problems, right? So we'll talk about what backtracking is and like things you should know about it, and then we'll kind of go over two problems. And I think these problems are really good in the sense that being able to solve these problems give you a lot of intuition about how backtracking works, and then ideally like a lot of other backtracking problems branch off of these ones. So I think these problems are like the best backtracking problems, and that's why we're covering them. And we'll just kind of like go through some final thoughts on backtracking and maybe some like advice on how you should approach studying for backtracking problems. Yeah, so with that, what is backtracking? So the like dictionary definition you'll get is like, with a particular solution in mind, you search and build partial solutions and then abandon the partial solutions if it is no longer valid. So the image you should have in your head is that we're searching through a solution space, right? So depending on what the problem is asking, there are multiple solutions, or there are like multiple, there are many solutions or a single solution, but there are many like potential solutions and partial solutions, and we're trying to figure out, we're trying to search this space to reach the answer, right? So oftentimes backtracking can ask like, for you to find all possible solutions to a problem. And so when you see that, that's definitely a flag that it is a backtracking problem. And we'll see an example of one of those today, and also like a non-example as well. And so it should feel kind of like a brute force in a way. And it's kind of not also, because we have this point that we will abandon partial solutions if they're no longer valid, right? So in a brute force method, like we won't care. We'll just like do as much as we can, like do everything, right? But what makes backtracking effective is that we kind of abandon solutions when logically they should be abandoned, right? So this is kind of like the graph that we have. So the question marks are like partial solutions, and then at each partial solution we can check if it satisfies like the constraint of the problem, right? So we're at some starting position, and then we go to some partial solution, and then say we take this upper branch, right? And going up a branch means that we are like updating the solution, as in like maybe this is like adding an element to a set or an array, and kind of like getting closer to what a complete solution might look like, right? So we're at this partial solution, and then we take another path, and then we find that this partial solution doesn't satisfy the requirement of the problem. So there's no reason for us to keep searching down this path, right? Because all other solutions that branch off of this one will not satisfy the requirement. So we stop there, and we kind of move backwards. And this is like the backtracking part, right? So we go back, and then we choose a different partial solution path to check. We find that, and then we find that we reached another dead end, right? And then when we go back, we see that there's nothing else to check, right? There's no other partial solutions to check off of this one. So we backtrack to the initial partial solution, and then we kind of keep going down this like search path, and then, right? So eventually we will like reach a successful path, right? And yeah, so this is like an interesting picture, because it wouldn't be very helpful if, say, like we happen to pick the right thing every time, right? So in some sense, backtracking, like depending on how you code your backtracking, maybe it solves a certain instance of a problem very quickly, and maybe we just were really unlucky. So this should kind of be like some sort of flag that the runtime for backtracking might be horrendous, because we need to do a little bit of like worst case analysis on that. Right. So that whole like graph and explanation should have felt a little bit like DFS, but a little bit smarter in the sense that we didn't go down all the way, right? We stopped prematurely. And then it should also feel exhaustive because we are checking a solution and then we're going to stop when we like we end up checking everything, right, until we reach a successful solution, right? So that's kind of like the spiel on backtracking. And then I'm gonna like motivate some other points about backtracking later, but does anyone have any questions or comments about backtracking? Cool. Yeah, if you do, you can just send it in the chat and I've got it pulled up. So, all right, so now we introduce our first problem, which is permutations. So you're given an array of distinct integers, and the requirement is to return all possible permutations of this array. So if you don't remember what a permutation is, we'll just go over an example, so don't worry about that. But outside of that, are there any questions about the statement of the problem? Yeah, it shouldn't be too bad. We'll just return them as a list of lists. Yeah, that like might be a question, but yeah, the statement of the problem isn't super complicated, so we're kind of lucky here. Right, so let's look at an example. So say we're given the array of integers 1, 2, 3, then all the permutations are 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, and 3, 2, 1, right? So hopefully you agree with me. But basically, each element, right, or each permutation is some ordering of the elements, and we just need to find all the different orderings, right? And the fact that the integers are distinct are really important because if they weren't, that would kind of be a mess. And yeah, hopefully, I don't think you would get that kind of question because maybe that's a little bit cruel. But yeah, so one thing we noticed, right, is that we have to return every single one of these lists, right? And whenever we tack on an additional element, right, the number of permutations grows exponentially, right? Like if we introduced a 4 here, we would suddenly have a lot more permutations, right? And so like one thing that we notice is that we kind of have no choice but to construct every single permutation, right? There's no way to like, there's no like smart way to like just suddenly have every single permutation in like linear time because you have to construct every single one, right? And you have to add every single one to a list. So that's unfortunately or fortunately, that is unavoidable, right? It kind of tells us how the algorithm should look. What it doesn't tell us is how it should be coded. And that's like another thing about backtracking is that usually the algorithm might be more obvious, but then the actual code is pretty nuanced. Right, so let's just like solve like an easier version of this problem. So say the input size is fixed, right? So say it's always 3 or always 7 or something. Then the question is, okay, if you know that the inputs is always going to be a certain length, then I'm going to claim that you can code this very easily, or like very, you can code this, you can make a very simple construction for this algorithm. So does anyone have any ideas? Like if it's always fixed at 3 or always fixed at some number every time, like what's a viable option? Yeah, so I guess if you were thinking, oh, we can just write that many for loops, then you're totally right. right? So you could just write however many for loops you need, right? All nested. And then at each iteration, you're basically choosing one of the elements to insert. And then the runtime would be like n cubed or n to the whatever, depending on what the fixed size is, right? So if the array was always fixed, we can solve this question pretty comfortably, right? And so that would kind of be n cubed, right? But like we kind of notice that this isn't super efficient because like say we're back at this 1, 2, 3 array, right? And say we fix like the first element here. We don't need to iterate over 1, 2, 3 again, right? We only need to iterate over 2 and 3, right? So there's this kind of idea that maybe we should thin the for loop out as we go deeper, right? So that's one thing that we should notice. Yeah, so yeah, I know like if it was always 3, then this would be constant time, but just play with me. Right. So now the question is, okay, if the size of the array is variable, then in some sense we have to add more for loops, right? We need to kind of increase or decrease the number of for loops depending on the size of the input, right? And I'm going to say that there's pretty much only one like coding technique that can like suddenly increase the amount of code that we have depending on the size of an input. Does anyone know what that thing is? Either you hate it or you love it, but you probably hate it.
Is it recursion?
Yes, it is recursion. Yeah. So maybe you're in the happy group, or maybe you're not happy to hear this. But basically, like I wanted to motivate that. Like this is the reason why recursion is so central to backtracking, because the solution space grows with the size of the input. So our code also needs to grow. So oftentimes, like some sort of recursion will be in the backtracking solution. Yeah, so we're already doing pretty well, right? So we know that we need to use recursion, and we kind of need to loop over a bunch of things, right? So let's kind of revisit that point of like thinning elements out as we go deeper. So there are kind of like two options. One is like the easier one to see, and then the other one is very, very slick and very clean. Does anyone want to take a guess at either of them? Yeah, so I think like the easier choice to see is we just have some sort of running list or running set of all the elements that are left, and then we remove one element from that set or list every time we proceed with the recursion, and then add it back when we finished like some recursion subtree, right? So we have something that just keeps track of everything that we're left with, right? And then there's like another option which we'll end up going with today, but is very cool. Okay, and the idea is that we can use the rest of the array, right, as a bank for the remaining elements. So that's kind of confusing, but like just kind of keep this word bank in mind, right? So basically, if we look at this, right, so we're looking at 1, 2, 3, 4, and so the numbers that are gray are what I'm going to say are in the bank, and then the numbers that are bold, and there's none bold right now, but the numbers that are bold are going to be the ones that have been fixed, and then anything that's underlined is the position that we're currently checking, right? So at each, right, so right now we're just looking at the 0th position or the first position in this array, and we haven't fixed any of the elements, right? So we have all of them as options. And what happens is we like go down some recursion and we fix one, right? And then we push the current position we're looking up, and that decreases the bank of elements, right? And so basically any recursion that stems from this, right, that is a descendant of this partial solution has one as the leading element, right? And so maybe another recursion branch would fix 2, another one would fix 3, and another one would fix 4 at the first position, right? But we'll just look at this kind of branch, right? So, and then from here we have to, well, eventually we'll have to fix all 3 elements at the first position. So maybe we'll fix 2 and then say we're done with that, and then we fix 3 at the second position, right? So again, like anything that is a descendant of this partial solution will have 1 and 3 as the first 2 elements, right? And so you can kind of see that the bank is already shortening out, right, as we go level by level. And then whenever we hit a complete permutation, then we can just create a new list that is equivalent to that and then return it. Right, so just to kind of, for completeness sake, right, so here we'll fix 2, and then again we'll fix 4 there, and then 2 is the last element in that branch, right? And right, we see that 1, 3 they're the first 2 elements here. All these have 1 as their first element, so this is hopefully checking out, right? But then there's kind of there's a strange thing where, okay, if after we are done with this 1, 3, 2 branch, when we go back, right, via the backtracking recursion, then suddenly we have to choose to fix 4 again, right? So we need some sort of logic that will swap the 2 and the 4 out, so that we can recurse on 1, 3, 4 instead, right? And that's kind of like the major question that we're going to ask is, okay, how do we kind of do this swapping thing in order for this recursion to work, right? Yeah, so basically we've already figured out that we need some sort of recursive function that loops over remaining items. And then, right, the question we're addressing is, okay, how do we swap the elements, and like what do we need to keep track of when we're swapping, right? And it seems like it can get really messy when we swap, but actually this is like kind of one of the beautiful things about recursion is that basically after the recursive call, if we undo all the stuff that we did, then we're in perfect shape, right? So as long as we undo the swap after we finish this recursive call, then we can freely go about with the rest of our lives, right? Is basically the story, right? So any questions about like kind of the thought process, right? So like at this point, you should like feel comfortable in like being able to step through a solution. It might be a little bit tricky to like manage all the base cases or just kind of all the edge stuff, but you should kind of have like a decent idea of how the code might look like. And then you still have to make some implementation choices. So any questions so far? Cool. Yeah, so this is going to be the permutation code, right? So at the top, we have the return list, right? Maybe it's, you can like pass this into the recursive function if you want, but here's just a global variable. And then here's the actual DFS function. So we'll look at this one first. So here we choose a parameter n, which is just the number of items, right? So this never changes. And then the list of numbers, right, is basically just the list of numbers, right? This list changes order, but it never changes, like the contents don't change ultimately, right? The ordering might change as we build different permutations, but the contents, like the actual numbers, are all in here, right? And then current position, right, just like how we saw before, current position will divide the array into 2 parts, right? So everything to the left of current position has been fixed, and we're not changing that below this subtree, right, below this recursive call. And then everything, including the current position and after it, is our like numbered bank, right, the bank of remaining elements that we have, right? So if this is the base case, right? So if the current position is n, that means all the elements have been fixed, right? Which means that there's nothing else to process. So we've found a single permutation, which means we can add it to the new, like the return value, right? And we definitely need to create a new array list for this, because if we don't, we might see some pretty undesirable behavior as we add the same list to a large list over and over again, right? So if you're curious, you can kind of play around with that if you want. But right, and so then the for loop, right? This is like these 4 lines are the bulk of the algorithm, right? So we loop from the current position to n, right? And so we already see that if we increment the current position when we call the recursive function, then our for loop kind of thins out as we go deeper into the recursion, right? So that part is a check, right? And then the first thing that we do is we swap whatever, okay, so this collections.swap basically takes in a collection or like a list, and then it swaps the items at current position and I, right? So you can like implement this yourself if you want, but it just made the code shorter. That's why I did that. So yeah, so the first thing that we do is we swap whatever is in the current position. So this is like the underline, right, that we're looking at with the I element, right? And then after we do that swap, that signals that we've like suddenly fixed this element, which means we should push on with the DFS, right? So we pass in n, we pass in the list, right? So we had just fixed an element, so we pass this in, and then we increment the current position, right? And this tells us that the bank has gotten smaller and we have just fixed an element, right? And then, like, this is kind of the whole recursive part here, but after we return from this function, right, for however much time later, we need to undo the swap, which is just the equivalent swap current position in I, right? And as long as every single recursive call like undoes the swap, then we'll be back to where we want to be, and then we can like continue with another iteration, right? So like something interesting that we notice is that the first iteration swaps current position with current position, which is fine, right? Because we need to fix the element that's currently there to proceed, right? However, right? So that's kind of the DFS part, where we search through and find all permutations. And then this is like the original function, right? So here we just are changing it to a list so that we can use the collections.swap method. And then, yeah, we call DFS on the length, the list, and then we pass in the current position 0 because we haven't fixed anything yet, right? So we need the initial current position to be 0, and then we return the return value. Yeah, so any questions about the code, comments? Yeah, so hopefully, I mean, I think that kind of followed the same logic that we did building up to this solution, despite the code being fairly short, right? So now here's kind of like the tricky part is the runtime, right? So maybe if you've taken a combinatorics class or probability class, or maybe you're smart, maybe you know the answer to what the runtime would be. And so I guess like one hint is that we have to make every single permutation, right? So any guesses or answers?
Well, the permutations are usually like factorials, right?
Yeah.
So because it's like you have n ways to fix the first one, and then n-1 for the next one, and so on.
Yeah, exactly. Yeah, so the n factorial is showing up, and yeah, that's pretty much basically right. So n factorial, and then I think there's like some deeper, unnecessarily complicated analysis that says it's actually between n factorial and n times n factorial. And like one thing we can kind of, the way we can justify this n times n factorial is that like we terminate whenever we reach a permutation. And when we have reached a permutation, right, then we create a new list of size n, right? And so that takes linear time because there are n elements, right? And we have to do this n factorial times, right? So kind of that's where the n times n factorial shows up. I think if you say either one of these, like you'll be fine. I like if the interviewer expects you to know that it's between these two, then you should work at a different company. But yeah, and I mean, I highly doubt that they know that either. But I think as long as you're pretty much in the ballpark, like that's fine. If you're saying like linear time or something or like log n, then that is no good, right? Yeah, n factorial, yeah. And then now kind of the next part is the space complexity. So there are like two ways you could answer this question, so either way is right. Anyone want to take a swing? Yeah, so there are kind of two answers, right? So if we count the solution as part of the space complexity, then we get n times n factorial, right? Because there are n factorial permutations, each of length n, so n times n factorial space for the return array, right? If we don't count the solution, then it's going to be O of n because the depth of the recursion is n, right? Because we need to fix n elements, right? And that's equivalent to n levels in the DFS tree, right? So those are the kind of two ways you could answer this. When you're kind of faced with something like this, I would always just make it clear like which space complexity you're solving for. Sometimes maybe the interviewer will ask for one over the other, right? All right. So that was kind of permutations. Any questions about that? This is like one of the problems where we have to find all of something or like all ways to do something. Cool. All right. So the next problem. Oh, okay. Yeah, actually, there's a comment about permutations. So there are some variations. Like one of them is instead of storing the results in an array and returning them, we can just print every single permutation. And then now you kind of ask like, oh, how does the space complexity change? Like, can I do anything to like improve the runtime or something? And I actually got this variation in an interview, which was interesting. But yeah, so just wanted to like throw this out here for you all to think about. Cool. So the next problem is like the other type of backtracking. And so the problem is word search. So given a 2D board of letters and a word, the task is to find if the word exists in the grid. So the way the problem is set up now, you should probably have a question. Does anyone want to ask the question?
I mean,
I guess
one,
like in general, go for it.
All the tiles have letters on them?
Oh yeah, all the tiles have letters. Yeah, so each cell on the board has a letter, and then we're also given a word, right? So I guess the question you should be asking yourself is, okay, what does it even mean for the word to exist in the grid, right? Just mean all the letters are there?
Or like, could it be like a backwards word or like?
Yeah, right. There are so many questions you could ask because of how big it is, right? So yeah, so a word can be constructed from moving to adjacent cells, right? So either horizontally or vertically, right? Um, and then another restriction is that you can't use the same cell more than once for creating a given word. So the input comes in as the 2D array of like characters, and you're also given a string. So let's just look at an example. So say this is your 2D board, right? So we have a bunch of letters here. And then let's say we're given the word A, B, C, C, E, D, and now the result is true. How do we see this? Well, we kind of have this path, right? So we can start at A, then travel along adjacent letters, right? So that's like the idea. And that is true, right? So we should return true if we get that string. And another example is SFCF, right? And we should return false. So if you're looking at this, if you're just looking at the grid, right, you should say, of course, we would never be able to do this because F only appears once, right, in the grid. So there's no way we can like suddenly cook up another F in the grid, right? Another way you can kind of reason through it is like if we start at S, right, either of the S's, but only one of them is adjacent to an F, so we have to go from S to F, and then there's only one adjacent C, but unfortunately there's no other unused adjacent F, so we can't make SFCF, right? So I think already at this point, there's kind of like a nice way to summarize the algorithm. And then the bigger question is, okay, how do you implement it, right? So if you're still kind of like wondering what the algorithm might be, one way to think about it is like if each cell is a room and the adjacent cells or adjacent rooms have doors between them, but you kind of can't see through the walls. And then now you're like someone in this house and you have to kind of like figure out if a given word is like, you can kind of construct a given word by like moving through the rooms, right? So like for the example, A, B, C, E, D, right, you would like start at, say this is the first room, and then you would just kind of check your adjacent rooms, right? You see one that has B, so you're gonna check, okay, I have A, B, right? And then if you open the door and you see F, you're gonna say, okay, there's no reason I should like continue searching, right? Because F is not the third letter, right? So you look at C, and then you kind of get lucky with opening some doors, right? And then eventually you reach D, and then you say, okay, this word is possible, right? So that's like a good technique to like think about an algorithm, and that's like pretty much the algorithm, right? So it is iterate over every cell and run some search function. I don't think there is an easier way to do it. If you've come up with something, then you should be doing some other things with your life, maybe. Because yeah, that like any kind of other solution is very unclear, right? So maybe you've discovered something new by kind of creating a new algorithm for this, but this is kind of all we have, right? Because we can't do any sort of like dynamic programming because it's unclear what any subproblem would be, and the problem is like pretty much posed in only one way, right? But that doesn't mean the problem is solved, because now there's still the question of, okay, how do we implement this in an easy way, a way that's understandable, and then one that also like avoids unnecessary runtime issues, right? And so the search function has to be recursive, right? Because like we said before, the word size can be different. So we need to be able to search further if the word is longer, and kind of the only option we have here is going to be recursion. You can do it iteratively if you want, but it's going to be a lot harder to keep track of things. So recursion is definitely the way to go for in general for backtracking. All right. So kind of any questions on like how we arrived at this conclusion that this is pretty much the only thing we can do? All right. So now the next question is, okay, so if we're writing some sort of recursive function, then what information does the search function need in order to be effective? So there are a few right answers or answers that I'm expecting. Anyone want to take some swings?
It definitely needs the current position in the list that it's traversing.
Yeah,
as
exactly,
well as
right.
which list is, if it's a multi-dimensional array, it needs to know which list is above and below, right? Or it
Yeah,
should know
so we
that by
kind of
its
need
current position.
access. Yeah, we need access to like the entire grid, right? Yeah, and then you said a few things, right? So yeah, we need access to the grid. We need to know like where in the word we are, right? If we're at the beginning of the word or the end of the word, right? That really changes what we should be doing. And then you also mentioned that we need like to know where in the grid we are, right? Which is like the row and column index of the grid. So yeah, actually that's like pretty much everything. Yeah, so row, column index, the actual string for the word, and then like what letter we're on in the string, right? I didn't include the board because I ended up just making that a global variable. I guess you could have done that with the word and string also, but yeah, so this is kind of like all the relevant information we need. Any more information might be a little bit overkill. Yeah, and then the next question is, okay, after we've like dealt with parameters, okay, naturally the next thing to do is write a few if statements at the beginning of the recursive function to check for base cases. So the question, right, is when should we stop the search? And again, there are a few answers here.
The two circumstances I can think of are, one, when we reach the end of a given word. If we've reached the target word, we should stop. And
Yep.
then two, if we've checked all parts of the grid around that immediate letter that we're on and find none of the subsequent letter, then we should stop.
Yeah. So yeah, so the first thing is totally right? If we finish the word, then we've solved the problem. We should get out of there as soon as possible, right? And the other thing was, if we've kind of like reached a disagreement, right, with the character and the current cell and the character in the string, we should stop. So I noticed like Nathan, that you mentioned like if the adjacent cells don't have the next character, we should not recurse down. So that's like oftentimes like a mistake when you're coding backtracking, because what you're doing is you're pushing on the responsibility of the next cells and the next letter onto the current cell, right? When we can just push that responsibility on the next cell and the next letter, right? So that's actually a really good point. So thanks for answering that way. And then, yeah, so there's like one other condition that maybe will become a lot more clear when you start coding, but yeah, I'll just like give a couple seconds if anyone wants to shout that out. Again, sticking with the idea that like the current call like only thinks about itself and very selfishly. Yeah, so I think if you're coding this, you would kind of run into this pretty quickly as an issue. But so one is when we finish the string. Second one is the out of bounds, right? If we go out of the grid, we should not keep going, right? And then if the character is wrong, we should also stop, right? And so these are all things that we can check on the current iteration, right? Right, we can just check if we're done with the string, or we can check if this current position, right, this row and column is out of bounds, then we don't do anything. And we can also check if the character is wrong, right? So we've actually like pretty much figured out half the function already. All that's left is the recursive part. So the question is, okay, how do we recurse on the neighbors? And then also, how do we avoid duplicating or using duplicate cells, right? So we kind of push this under the rug a little bit, but it's back. So any ideas on either of these? Yeah, so maybe this first question was kind of like poorly posed, but we only have one choice, right? We just recurse on the top, like bottom, left, and right. So that's that part. So if you were thinking, okay, this is, I don't know what he's asking, then you're probably thinking the right thing. And then now the question is, okay, how do we avoid using duplicate cells? So this is like the very slick answer for word search, just like how permutation used like the rest of the array as the bank. Word search uses, it's not like a similar technique, but it's kind of this particular feature that is convenient to use. Any ideas? It's like kind of cheeky, maybe you could say. Yeah, so one option is we can just change whatever, you can change the character in the cell to like some reserved character or like some character that's not in the alphabet. And then that basically eliminates the ability to go back and check that, right? If you're not able to modify the input, so like sometimes that's the case in an interview, you're not able to modify the like 2D grid, then you can kind of keep track of positions that we've seen so far and then just make sure we avoid those same positions in the future, right? Yeah, so this is kind of makes our lives a lot easier though if we get to do it this way. And so now basically like the search function is pretty much done, right? Are there any questions before we like actually see the code? Cool. Yeah, so I guess one other thing is like we have to just make sure that we restore the character, right? If we just suddenly start changing every single character in the grid, then we might just not solve the problem, right? So we just need to make sure we restore the characters after we've changed them, right? Okay, so we'll just look at the search code, the search function. The rest of the code is pretty simple, so we don't need to go over that. But so here we have the board up top, and then again, like the row, column, the word, and the current index, right? Yeah, everything we mentioned before. And then we have our three base cases. So, right, if the index has passed the word, then that means we have completed the word, right? So return true. And then if we're out of bounds, return false, right? And then if the current cell doesn't match the current character at the index in the word, then we also return false, right? And so just in general, when you do this backtracking stuff, you should always kind of push the responsibility of checking things to like as far back as you can, right? Like instead of checking if the neighbors are out of bounds, just check if this particular call is out of bounds, right? Likewise for this. And the order matters very much, because if we did this, if we checked if the characters matched before it was out of bounds, then we could just end up being out of bounds, right? And then we would get an error in the code. So this ordering matters, right? But basically, after we've reached this point, right, we can kind of use the fact that the row and column, right, the current cell matches, right? Because if it didn't match, we would have returned false and not have reached this point. But now we know that the current cell matches the current letter in the word, right? So we just kind of keep some temporary variable for the return value of the recursion. And then here's like the changing the current character, right? And then this is like something you'll see very often in any sort of like grid search algorithm, is that we have the offsets, right? And so we can loop over the offsets and then just add the offsets to the position, and that way we can recurse down the different parts, right? So columns offset, so 0, 1 means that we're searching to the right, and then this is we're searching down, and then we're searching to the left, and then we're searching up, right? Right, so we iterate over each of the offsets, right? So there are 4 offsets. And then we just call the search function on the row plus the row offset, the column plus the column offset, the word, and then we increment the index, right? And if at any time we've seen that the return value is true, then we just stop recursing because we don't need to anymore. Right, so that's just the recursion part, and then here's the undo part where we say we restore the current cell of the board to whatever that character is. And we can do this because, right, remember that we've guaranteed that the cell in this board, the cell at the current position, matches the letter at the current index. So we're able to kind of use the word to restore this character. And then we can just return the return value. So any questions about the code? Cool. Okay, so runtime. So, right, when you're thinking about runtime for backtracking, you always want to imagine the absolute worst case possible, and then that's pretty much your runtime. So, any ideas for the runtime? This one's a little bit more nuanced than the previous one, maybe. Or maybe what's like a really bad example that would just cause this code to run for ages?
If like a bunch of copies of this, like the string, but like -1 character existed, it would take forever to search through.
Yeah, exactly, right? So the bad example is every single letter in the grid is the same. The word is the same as well, but the word just has one more character, right? That's exactly the worst example. But now the question is, okay, how long would that take? Yeah, so there are kind of 2 parameters, right? There's like the number of cells in the grid, and there's also the length of the word, right? Yeah, so basically, one thing that we noticed, right, is that since we have potentially have just come from a character, right, in general, there are only going to be 3 children, right, at any point. Right, so kind of the number of recursive calls we have to make in the worst case is going to be, right, the size of the word cubed, right, because there are going to be 3 children at every call, and then right, and then that many, right, so L cubed is the number of leaf nodes, right? That's just like some binary tree or trinary tree stuff, ternary tree, right? So O of L cubed for the search function, right? And then N times L cubed, right? Because every cell we need to call the search function. And then the space, right? As we've seen before, the space is just the depth of recursion, which is L, right? So yeah, so I mean, if this part was a little bit confusing, then just kind of like review the tree stuff. Yeah. Any questions about the runtime or space? Yeah, so chances are we will usually hit a better runtime depending on the algorithm or like depending on the input. But this is like the absolute worst case, so we have no choice but to meet it, right? So yeah, that's been the word search problem. So kind of like just to wrap up with the whole backtracking story. So permutation and word search are like two types of backtracking problems that I say make up like for more than 60% of the backtracking problem styles. So I think if you are very comfortable with how we reach the solution to each of these, then that should be a really good starting point for you, just facing any other backtracking problem, right? So other point is like, it's not worth being an expert in backtracking, right? So if you just study backtracking every day, that's not the most efficient way to go about studying, because you're more likely to get another question than a backtracking question. So your time might be better spent doing like a tree problem or something. But so yeah, that's kind of like the point on backtracking, right? I guess I would also say like, if I were an interviewer, I probably wouldn't ask a backtracking question because they would just end up being a mess. And I don't know if people, like most people, feel that way too, but that's just kind of like my 2 cents. But if you're in the position where you're given a backtracking problem, like the best advice I have is to like follow kind of like the structure that we've outlined, and then like just keep your code very clean, right? Clean and organized will make the backtracking very, very smooth, right? And then for the analysis, right, just like be in the ballpark. Like don't give like linear time run times for things that are very much so not linear. And just like kind of try to hit the like rough idea, right? You can kind of like we were a little bit like hazy with a lot of the points when we were doing the runtime, and I think that's fine, right? As long as you kind of see the main idea there, right? So there are some other backtracking problems. Some of these are really hard or really long, so like I'm not saying you have to do these by any means. The 201 APTs are really nice backtracking problems. I think they were optional, so there's a decent chance you didn't do them. So maybe you should do them. But yeah, so that's it for backtracking. Thanks for listening, and thanks for participating, everyone. Appreciate it.
Thanks so much, Dorian.
Yep.
For real.